All right, come back. Introduce. Today we have our own Sheldon Landsberger here at the University of Texas at the Department of Mechanical Engineering. He is the Robert E. Trull Chair in Engineering. Of course, his specialty is nuclear engineering, which will be his topic today. Title of his talk: Naturally Occurring Radioactive Material in the Oil and Gas Exploration Field. And let's put one second. A little background on Dr. Landsberger. As I already stated, he's professor of mechanical engineering here for the nuclear and radiation engineering technical area. He's been here since 1997. He has 260 peer-reviewed articles, 195 conference proceedings, surpassing me by quite a bit. Mainly, he has studied nuclear analytical measurements and their appropriate and their applications in nuclear forensics, natural radioactivity, and environmental monitoring, trace and heavy metals. So we'll hear a little bit about that today. He's been working on radioactivity measurements in the oil and gas exploration field for 13 years. So a little abstract on his talk today. First, radioactivity measurement in oil was first discovered in 1904, University of Toronto. Short 8 years after the discovery and radioactivity in 1896 by Henri Bequerel. I could try that. It was not till 1980s that the beginning of a multitude of investigations began in characterizing radioactivity in many aspects of the oil and gas industry. More than 100 million barrels of oil produced every day worldwide. The environmental impact can have environmental as well as health-related concerns, especially for the workers. The presentation will give some historical overview of this and how the residues left behind should be monitored. So with that said, switch presentations. Let's welcome Sheldon Landsberger.
We're getting on back to the first slide.
Yeah, hit that. See it works.
This one?
Yeah, there we go.
Okay. All right. It's always very nice to come to a symposium like this. This is going to be pretty non-technical. I always enjoy having this. However, having two of my colleagues also coming to my talk always makes me a little bit more nervous, to say the very least. So just recently, Justin Nobel came up with a very highly charged book called Petroleum-238. And what I'm going to try and do is to give you a bit of an overview, plus historical overview, and an environmental impact of a norm which is called naturally occurring radioactive material in the oil and gas exploration field. Perhaps the first oil rig in the world came in 1859. Native Americans knew about oil seepage for hundreds of years. Europeans became aware of the existence of petroleum in the 1600s. Mineral oil was used primarily for medicinal purposes and was reputed to cure many ailments, including rheumatism and arthritis. And here's a picture of Edwin Drake. He had 21.2 meter deep. An engine house and derrick were constructed, and Drake purchased a 6 horsepower, or more commonly known as 4.3 kilowatts, horizontal, and that should be steam engine and not stern engine. Sorry for that typo. So we think that this is perhaps the very first one in the world. Well, one of the very first papers on norm in oil and gas came from the real UT, where I graduated from, University of Toronto, of course, right? Out from the Great White North there on the island. And he presented this work at the transactions of the International Electrical Congress in St. Louis in 1904. And his talk or his presentation is on the radioactivity of mineral oils and natural gases. And you could, it's kind of amazing how many of these have been actually archived now, and you can actually go ahead and download that on the internet for a price. Okay, so let's talk first about world electricity energy needs. Obviously, this is not a real picture. This is a real picture which has sort of been put together. And as we all know, as the standard of living goes up, electricity needs go up as well. And we also know that in the past 3 or 4 or 5 years, electricity costs have really risen tremendously, certainly much more than the cost of living that there's been around. Okay, here's a picture from a satellite of North Dakota fracking. Right? Any of you know what fracking is all about and how the gas sometimes goes up? And what happens with the gas? Well, they don't cap it, right? Because it's too expensive to cap it. And sometimes it just keeps on burning 24 hours a day. And that is in a very isolated place. And so you can see the amount of light which comes from this fracking field almost is as strong as many parts of the eastern USA. So this is an old picture, but it hasn't changed all that much. This is the United States producing oil and gas wells, and we all, really very know this. There's some out in California. Most of it is in the western states, in Texas and Oklahoma. And if you look on the right-hand side, you can see the natural gas production as well. Of course, wherever there's oil, there's also gas. So if you look, I have a first-year course called FIRE, which is Freshman Introduction to Research and Engineering. And the students take certain topics. Sometimes they don't have the topic which they want. Everyone wants to do robotics, Dr. Pryor, but I have to fight against that. And so as such, this particular project is that they have to go ahead and look at the environmental impact of the main sources of electricity out in Texas. We have about 4% that comes from solar, 4.35% comes from nuclear. That may change in the next few years. It's a staggering 25% comes from wind energy. And of course, there's coal as well, about 20%, but that is going less and less every single year. And the main part is of gas, as we all well know. Okay, there are about 100 million barrels of oil each day is produced. Every 10 days, 1 billion, or in the European style, 1,000 million barrels is produced or consumed. That's 36 billion barrels a year. So if someone comes up from the great state of Alaska and says, we have found 18 billion barrels, that's only a few months, right? So oil is used quite a lot. USA uses about 20% of the oil production. Does anyone know out of every barrel how much or what percentage is used for gasoline? A guess? Even a bad guess? 45. Perfect. It's actually 55. But you got it. Okay, so that's really very good. So in other words, if every car became electric, right, we would still need to have oil because we use oil for everything, absolutely everything. Our standard of living actually depends on oil. Everything from the oil which comes into some of these covers for smartphones, all the way out to rubber, and in a lot of industrial applications, which we depend on for our standard of living, comes from oil as well. The expanding economies of BRIC, Brazil, Russia, India, China, Southeast Asia, and of course the Middle East, will probably need to have more oil as well. Much more oil and gas may be needed for the foreseeable future. Political weapons, at 75 years old, I remember very well the 1973 oil embargo, people standing up in line for a very, just to get a few gallons of gasoline. The latest would be the gas from Russia to Germany, right? So there's a political problem. Are you smiling?
I'm from Germany.
Well, there you are. So you're not laughing at me.
No.
No. Okay. So we know what's going on there with former Merkel, doing all these types of deals. I should keep them on. Introduction. Natural occurring radioactive material, NORM, sometimes called T-norm, which means technologically enhanced, still remains a problem in the oil and gas exploration industries. Radioactive wastes from oil and gas drilling are incorporated in the drilling mud, sludge slimes, or evaporation ponds of pits. Radioactivity can then be concentrated in mineral scales on the pipe storage tanks and other extraction equipment. And the top two radioactive species which are monitored are the infamous radium-226 as well as radium-228. And all of their daughters are the primary radionuclides which are left in the waste. The sludge, the radioactivity can be in the soil, scale, and sludge. Soil through condensation, scale with formation along the inside of pipes, pipelines, sludge deposited at the bottom of storage tanks and separators. And this would be a typical pipe which you would see completely crusted over with radium-226 and radium-228. With a lot of other chemical constituents, which I'll talk about later. Here is a Montana landfill for oil field waste. We're not talking about a few millimeters here. We're talking, it being pretty high. And of course, the more of this scale which you have in an oil pipeline, then that means that that pipeline is not really very efficient. So a lot of time and a lot of preparation is done to try to reduce this scale that you have in the pipeline. So a little bit about the geology. Uranium-238 and thorium-232, which are stable radionuclides. Uranium-238 has a half-life of 4.5 billion years, are naturally present in the Earth's crust and mantle. They are found in small amounts, 1 to 10 micrograms per gram, parts per million, and typically are not significant components in other minerals. The geological locations, what you have is the shale tends to absorb radionuclides and act as a trap for these hydrocarbons. The deposits can be located at the boundaries of the sandstone layers. Of course, the geology in West Texas will be different than geology in Ghana or in Ecuador, or in many other parts of the Middle East. So but that's basically a bit of an overview of the geological formation that there is. So the decay products of uranium-238 and thorium-232 are radium-226 with a very long half-life of 1,630 years, and radium-228 with a half-life of 5.8 years. The uranium-238 and the thorium-232 are totally insoluble, and they usually remain in the place of the formation. But what happens is that down the chain, which I'll be able to explain later on, you get radium-226 and radium-228 in the chemical 2+ state, and they tend to go to where the petroleum is. They are much more soluble than their parents and are then mobilized by the liquid. And radium in itself has an infinity for crude oil. Oops. And here what we see is animation where the uranium and the thorium would be embedded, and all its radionuclides would be able to come out, and the radium-2+, either as radium-228 or 226, gets extracted out, and then it goes out into the gas oil separator, the water, the oil, and also goes down. Also, what you have in the gas fraction is you have very little of the scale, but you have a lot of radon. And in fact, if you go into your home and if you have a gas stove, every time you put it on, get an itsy bitsy teeny weeny amount of radon-222, which gets into your house. So a little bit of a primer of radioactive decay, something which is taught in high school, but probably chapter 35 or something like that, so no one ever really knows. Uranium-238, its decay chain goes to thorium-234, protactinium, then out to uranium-234, and finally it goes out to radium-226. And this radium-226 is the one that gets involved in the oil, in the petroleum, plus all of its other daughter products. And the daughter products include radon, polonium, and lead to tin and bismuth, et cetera, until it finally goes out to a stable 206. You have the same thing in the uranium-235 chain. Uranium-235, as we all know, is the isotope which is enriched for power plants, including weapons of mass destruction, which is another topic that I can talk about later on. Okay, and in there you have the radium-223, which comes out as well. You also have the thorium decay chain. All of the thorium in the world has thorium-232. It has an extraordinarily long half-life, 1.9 times 10 to the 10 years, and its first alpha decay was radium-228. So as long as you have uranium-238 and thorium-232, which is in a geological formation, it'll always decay out. Okay, so it's always happening. Okay. Oh, well, here's a pop quiz question, which has nothing to do. Where does helium come from? You can't buy it on Amazon. Well, maybe you could. Where does all the helium in the world come from?
Amarillo.
Most of it, but how does it get there? How is helium produced? How do you extract helium? Well, all the helium in the world comes from radioactive decay, the alpha decays, right? There's no other way of being able to get that, and you have to extract it out. So every time you get helium and put it into your balloons, or you have a balloon that Albuquerque Balloon Festival or something along those lines, that's where all the helium comes from. And it doesn't get, and the only way that it gets replenished is by the more of the radioactive decay. Okay, so why radium? Well, first of all, we have Marie Curie, an amazing person who left Poland. She came over to work as a nanny and made her way through to becoming one of the most prolific scientists ever known at that particular time. There are dozens and dozens of pictures of her, and only her as a female, and everyone else being male, of course. And radium was later found out that it could be actually added to clocks. It would fluoresce. And there's a book, and I maybe even a movie, although I'm not too sure, about the Radium Girls. These were the women that went ahead and put their brushes inside the radium, and to make sure that the brushes were really very thin, they would then put the brushes into their mouth, make sure that the brushes were thin, and then later on they would get all types of cancers, particularly of the throat and the jaws as well. So that's the real concern of radium, as well as radium was used for a whole bunch of ailment hoaxes and things of that nature. All right, let's get down to the chemistry of the scale. Well, if you look, if you remember your high school chemistry, it's been a long time for me, so I have to look at the table of isotopes as well. You can look that radium is in the same group element as barium, strontium, calcium, magnesium, and beryllium. So typically, when you look at the scale, it's a combination of barium, strontium, calcium, and SO4 as a sulfate, plus added to it all the radium as well. So the radium can then also attach itself, because right now, all this being 2+, magnesium 2+, calcium 2+, they all try to go out to the same place as the radium. So there's a competition. Okay, we all know what West Texas looks like. Everyone here not in West, anyone here not ever visit West Texas? 1, 2, 3, 4, 5. It's worth it. Just one day, just go out to Midland for a day or two. Get the culture out there. Okay. That's me on the right-hand side, trying to be brave. I had to wear all this equipment. It was 103 degrees that day, and I'm sure my body must have hit 120 or something along those lines. So there's a lot of action which goes out there. We have about 12,000 wells out in West Texas, and they all have all types of radioactivity, which is part of it, particularly this one, which is in the oil and gas separators. And actually, when the work here, you can see the radioactive sign. And as well, what you need to have is that when workers work in there, it's in a very confined space. So the first thing that that they have to do out there is the decontamination of equipment. And there are multiple types of procedures which are done out there. These are people who work out there, and of course, there's a socioeconomic problem which happens when the price of oil goes up. Everyone has a job. Price of oil goes down. People are laid off very, very quickly, and all the other types of problems which go along with them, including social problems, drug problems, alcohol, and all that type of stuff. It's certainly very well known phenomena. It's sort of like the fishermen out in the east coast of Canada. They're really very busy in the summer and the winter. Well, they don't do too much and get all types of problems as well. Site specific. There's not one shoe that fits all, right? Every particular site has its own type of environmental cleanup that it has to look at. You can have a needs assessment, a design, a launch, implementation, and then an evaluation. There are some pretty strict rules which have to be followed. The further away you are from the TCEQ, then the more that you can get away with, more or less. And that's kind of worldwide as well. You have to have a safety program, radiation training seminars. You have to look at time, distance, and shielding. Of course, for the workers, they don't want to spend too much time in front of any sort of radiation. The further away you are, it drops off as squared. And any type of shielding which you have is also quite important. And there's also ventilation, and particularly in some of the areas. So here you see a worker looking at a plant, and here he has a meter which is out there to be able to see what the radiation is. Decontamination techniques. The effectiveness of decontamination is usually measured with a decontamination factor, no big surprise, defined as DF as the initial activity divided by the residual activity. Choosing the right type of intervention must be taken into account. You want to look at the type of surface to be contaminated, including roughness, porosity, coatings, radiological conditions, capability of treatment and conditioning of any secondary wastes. Well, there are three major types of decontamination. One is chemical extraction, nasty. The other one is mechanical abrasive techniques, which can be nasty. And the third one, of course, is high pressure water jetting. And the chemical extraction or dissolution uses a variety of chemical agents to remove the contaminated sludge or scale from the three types of the equipment. Remember, often this equipment, there's a lot of scale in it. And when these very large and very expensive pieces of equipment can't function well, you have to clean it up. Otherwise, you just leave it into the field. And that's been done as well, right? This can include, but not limited to, non-corrosive reagents, dilute acids, alkalis, aggressive chemicals, such as strong acid and other corrosive reagents. Because the first thing you think about it, trying to get rid of something, is this: hey, let's throw hydrochloric acid on it, or let's throw nitric acid, or a combination of the two. So that's been the thought that's gone on for many years. There's mechanical abrasive techniques that are physically remove the norm material from the contaminated equipment. Of course, you cannot do all types of mechanical systems in places which are really, really hard to get. This piece of steel, you can actually go ahead and get rid of most of it, but quite often you can't get rid of all of it. Some of the things which you have to include, including brushing, shot blasting, abrasive jetting, and typically the blasting techniques use an abrasive material that is used to clean the surface of the object being treated. Now, as you can well imagine, it is pretty tough to do that during the summertime. The high pressure jet water jetting uses an ultra high pressure to remove the norm material from an object. And then fortunately, or unfortunately, as the case may be, you want to be able to take any of the stuff which has sort of gone away, collect it, and then manage it. So this is our enemy. In this particular case, it is the scale inside the pipes. So a scale inhibition treatment is used to prevent scale from forming on the inside of the pipes and the equipment. And this would be analogous to the drip method, right? Drip method that is sometimes used in irrigation. Scale can be treated by the above mechanisms, but many companies choose to have a chemical treatment to prevent the formation of the scale. The treatment prevents the scale from adhering to the pipes, and the radioactive material remains in the produced water, which is very common in the oil industry. There's another method which is used, and that's called the ion exchange treatment. Ion exchange treatment is used to control the water chemistry, produced water as well. A resin is used in which the contaminated water passes through a column. Ion exchange, which removes the contaminants from the water. Process is being tested and for removing radium from water as well. The other aspect, what you want to do is called volume reduction treatment. So the volume reduction treatment reduces the volume amount of radioactive material into two separate piles. This type of treatment is done on sludge and can reduce the volume by up to 80%, but you still have to do something with this stuff. Decontamination process must be performed in a controlled manner in order to, number one, prevent the spread of norm contamination. And you can see a lot of people use personal protection equipment, ensure protection of the worker, minimize waste from the decontamination process as well. There are some automated decontamination systems, and this particular systems should be used wherever it is possible. This can significantly reduce the hazards to the employees. This is most important when working with water jetting operations, and whether the decontamination system is automated or manual, the safety and the proper personal protective equipment, mainly known as PPEs, must always be used. Remember, a lot of the workers who are in the field, right, these are seasonal workers. They don't always understand the rules and the regulations, and they also always don't follow the instructions. There's another way of doing decontamination, and that is mobile units. Decontamination can either be done at a fixed facility where you take the equipment and bring it to the facility, or a mobile decontamination unit. The mobile decontamination units have been used or are used to treat the norm-contaminated material, and they can include trailers and waters, PPEs, and you have sort of like a roving a team that goes from site to site with these mobile units. Operating criteria include that the purpose of norm decontamination is to eliminate or minimize radioactivity left on the equipment. That is really key. You want to make sure that your equipment is almost as good as the day that you bought it. Some of these pieces of equipment, they're $300,000 or $400,000 a pop, and so you want to be able to make sure that they work well. And they must be met to consider the equipment decontaminated. All equipment must be visibly clear of scale. That doesn't mean that it's been completely decontaminated, but maybe 95, 96, 97% has gone away. There should be not any detectable radiation on the equipment above background level. So what you do is you take your radiation detector, you go away about 200 or 300 feet, see what the natural occurring background levels are from the uranium and the thorium and all the decay products of the soil. Then go back in, see what the background levels are, then go up to your piece of equipment, measure it, then take away whatever backgrounds that there is. You have to subtract that out. After the decontamination procedures are done, you have to go back and see that you're less than the acceptable legal limit. There's a main change room, allows access to radiologically controlled area where the normal decontamination will occur. There's a handling area, reviewing the inventory and material, radiation surveys of equipment, an area to keep dirty, radioactive, and clean items separate from each other, and the quarantine area for any equipment that needs any further decontamination because the first time it didn't work out. There's a strip down area for the process of equipment such as valves and wellheads. There's a burning bay. This allows for any oxypropane or grinding of the equipment. And this area is where airborne normal contamination. The required operating criteria for a norm key decontamination facility, where you have wet jetting area. This is an area that can also have airborne contamination. If you look at anything at the body's respiratory system, the smaller the particle which you have, the deeper it'll go into your lungs. So anything which is 2 microns or less goes deep into your lung. That's why if you ever went to a bar where people were smoking, although it doesn't happen too often these days, right? And all of a sudden you go in and you're having trouble breathing. That's because all the smoke particles are less than a micron. They're about 600 or 700 nanometers, and they go really very deep into your lungs. So this area, as I said, can have the airborne contamination. So HEPA filter extract ventilation system should be used. A local extract ventilation should also be available to help control the dust and contamination. And workers are required to for proper respiratory equipment, which is not inexpensive, such as supplied air. The floor needs to be impermeable and non-inflammable, that is able to withstand some pretty heavy loads. The required operating criteria for liquid recirculation. Any liquid used for the decontamination process should be filtered and reused. There should be no external drainage system in the area to prevent decontamination. So if you use water or any other type of liquid substance, make sure that it stays on site. Don't put it down in the city sewers or anything like that. And you should have a primary supply tank, a filter bank, and a settling bank as well. The liquid recirculation system, the purpose of the system is to basically separate the non-contaminated sediment and oil waste from the produced water. So there's a really enormous amount of water is generated as produced water. There've been all types of thoughts in design of taking this produced water and really cleaning it right up so it can be used again in agricultural fields. That still hasn't been, it's been proven in the lab, but it certainly hasn't gone onto a full scale. The water used from the high pressure water jets will be circulated back into the system. You need to have the leak detection system in place. The settling tank is accessible and easy to remove any sediment. And the system should also have the capability to transfer water from a settling tank onwards. Control of the equipment. The system is required to control and track the progress of all the equipment entering the decontamination facility. This is just a list of some of the things which you may be able to see. Monitoring of equipment, serving equipment should only be done by personnel trained as RSOs, radiation safety officers. These are the people who have the type of training and they can oversee. And quite often you have a radiation safety officer coming out with the crew to make sure that the first days or the first hours or first few days, all the rules and regulations are kept. All norm survey equipment should be calibrated. Usual stuff, pre-operation checklist, monitoring contamination sites as well. That's standard operation procedures which you have in any type of lab. Personal decontamination should be done if employee has norm contamination. Monitoring of employees means frisking out, taking a radiation monitor after the clothes are off to make sure there is nothing residual on you. Decontamination process of an employee must be done in a manner that has reduced the radiation exposure, particularly to inhalation, ingestion, and absorption of radioactive material. For the most part, this is done really very well, but if you stay lax with your controls, and if you don't have continuing education every year or every other year, and you have a whole bunch of new people coming in, this is a very fluid, pardon the pun, this is a very fluid environment out here where you get a lot of people coming in for very short periods of time and then leaving afterwards. So safety first, safety is everyone's job. Just to give you a little bit of idea, this particular table comes from one of my publications when I looked at how much radium-226 and radium-228 there was worldwide in gas, in produce water, in hard scale, and in sludge. And this is given in becquerels per kilogram, which is a standard way of being able to give these types of units. Just to give you an idea, one site may have a sludge of only 50, and the next site may have a concentration of 800,000. If you're looking at hard scale, anywhere from 100 to 15 million. So every particular type of site, every different type of geography, every different type of country which is out there may have, based on the geology, how much uranium, how much thorium, and the way that the earth movements are around, there may be different concentrations that get into the petroleum. So as I said before, there's no one shoe that fits all. You can also have a dose assessment of norm, inhalation, and ingestion. You can start off with inhalation of respiratory tract model. You can look at all the lymph nodes, the transfer compartments, the liver, the kidneys, the urine, other types of organ. As soon as something gets into your upper respiratory tract, and then is really very small, particularly radon, which comes from radium-226. There's virtually no problem with radon in the open field. It dissipates very quickly, obviously, but you start getting into contained spaces where there's virtually no window and you have to come in with all types of respirators. That has to be done. Any types of ingestion is really pretty good. It goes into your GI tract and it goes out with your feces. In conclusions, the chemistry and radiochemistry of radioactive species in oil waste products is really horrifically complex. You don't have only the hydrocarbons and the gas and oil, but you have the radioactivity, which is part of it as well. Typical assumptions of equilibrium are not valid. And if you really want to understand what the movement is, you can get a couple of very good theses and PhD dissertations out of there. There's a plethora of papers out there dealing with this right now. And I know it's been a little bit on the short side, but I wanted to give you a little bit of an overview of some of the historical aspects. Go University of Toronto, right? And all that good stuff. And hope you've at least expanded your mind a little bit on this. Thank you very much.
Okay, questions? Of course, me, all right.
Yes, sir.
I could ask a million questions, but so it's mostly the radon 226 and 228 that you're worried about, is that right?
Yeah, you're worried about three. You're worried about the radium 226 and the radium 228, particularly the radium 226, which has a half-life of 1,630 years.
What's the radiation? Is it the gamma?
Alphas and gammas. Alphas and gammas. And the radium 228 is basically betas. And radium 226 decays into radon, which has a half-life of 3.8 days. And if you're in a confinement of that,
What's radon? That's the stuff that's in my basement, right?
that's right.
It comes from radium?
You did not know
I
that?
don't know anything about nuclear engineering.
No, all you mechanical engineers in the Walker department and I just don't.
This is being recorded.
No, but quite seriously, yeah, that's where it is. 50% worldwide, particularly in developed countries, 50% of the radiation which you get naturally occurring comes from radon. Because we spend 80%, 85% of our times indoors. But particularly during the
I
summer.
didn't answer my question. What's radon?
Radon is a gas.
Okay, what is it chemically? Is it radium?
No, it's not radium.
What is it?
Radium 226 emits an alpha particle and it goes to a radon, and that radon is a gas. It's in the decay chain.
So it's an isotope of radium then?
Yes. No, I mean they're all isotopes. Some are stable isotopes, but these all are all radioactive isotopes. They start off with uranium-238 and thorium-232, and they all go down. And they all go down the chain. So we are surrounded with radioactivity all the time. By the way, do you know what is the most radioactive part in front of ETC?
No.
Sculpture.
Huh?
Orange sculpture.
No,
Okay.
it's where everyone eats because of the stones. There's a whole bunch of stones out there, right? And they are have a radioactivity which is slightly higher than the norm. So if you stay there 24 hours a day and eat and all that type of thing, yeah, right down there. So we have that. I've also had a fire group from my class go down and look at the radioactivity in the ETC building, and lo and behold, the highest amount of radioactivity that they could measure was on the ground floor, because that's the closest to the ground where the radium and the radon is.
Let me ask a follow-up there. So one of your last slides was something that, if the person decontaminate the person, one of the procedures. So we're worried about radium getting into people, and then you said, well, if you ingest it, it comes out with your feces. So what is decontaminating a person?
Oh, you cannot decontaminate anyone if they've ingested it or inhaled it. Remember the miners back in the 30s and 40s, the uranium miners out in New Mexico and Utah and parts of Canada, they would go down low, very low, and there'd be a lot of uranium. And they worked there 5, 10, 15, 20 years, and a lot of them would get lung cancer because of the radon, which they.
I mean, how big a problem is this in the oil and gas business? Every oil well have to be contaminated in this way, or is just
I don't know if every oil well has to be contaminated, but for certain what you need to do. West Texas is a pretty dry place, right? Now you look at the problems that they have in out in the Gulf of America, or is it Gulf of Mexico? And so you will see that there is contamination which comes in there. But of course, the ocean is really large, and so everything gets diluted. But in many other parts of the world where oil and gas come, like from the jungle areas or from areas which are really very wet, that can immediately pose a problem. It basically has to be monitored, taken care of, and safety. If you follow those three and get the alarm as low as reasonably achievable, that's the main thing. You just don't want to have a lot of people going there who aren't trained and don't have the proper
So
people.
all wells in Texas are monitored for this?
They should be monitored all the time.
Should be, are they?
No comment. I don't want the government coming out.
All right, other comments? I can point you to past energy symposium discussing similar topics, but yeah, the question in the room.
Can norm be reprocessed and used in other things?
No, it can't be, not really, you have to bury it, sort of. But radium-226 has been thought to be a source to have a nuclear reaction to produce another isotope for nuclear medicine, but that's a different story. No, there is a lot of the stuff. It's 100 million barrels per day, 1 billion every 10 days. So it's there. It just has to be monitored well and train the people well. There is no free lunch in there.
Where do they bury it? What is the criteria of burying?
Some of them take it, they inject it back into the well. Others kind of leave it on site.
I think I
Oh, wow.
I have a similar question online here. I'll ask you to come back.
Oh, sure.
It's sort of for those who have driven through West Texas, this person is recalling that you will basically drive through some smelly air. So you seem mostly talking about solids, liquids, but it's
The smelly air basically is H2S.
But whether it be radium in the air or it has to be.
No, it's very unlikely to be radium in the air. Right?
Okay.
But H2S is pretty nasty.
Right. All right. In the
Sorry.
room.
Yes, sir.
Green and then the.
Can it be predicted ahead of drilling? I mean, like, do you get equipment on board if you think they're, you do analysis of regional wells?
Yeah, possibly. You could use some AI for that, but you would have to spend a lot of time and effort and to sort of get a map. US EPA has done a radon map across the United States, but I don't know if anyone's ever done a radioactivity map for in the oil and gas business.
Just surprised if it turns out to be kind of higher than you thought, that you have to immobilize the equipment.
Yes, yeah. It's very hard to predict the geology. I mean, we always think of the formation as being, hundreds of thousands of square kilometers or something. It's not. It changes all the time.
But you expect to find it in core samples that are stored in repositories still.
Yes, yeah,
Okay.
definitely.
Does
Snap
it
it out too far. All right. The left, yeah. Good sense.
Oh, sorry.
Yeah.
Who owns the waste? Does the company own?
The company owns the waste. Yeah. No, you had your chances.
Oh, yes.
So burying these materials or leaving them there, are there any long-term implications of that? So it's seeping in the water reservoir or something?
We don't have a lot of leaching out, which happens out in West Texas, right? But I think the main focus of this has to do with a lot of the workers who are out in the field. But as I said, in different parts of the world, the impact depending on what the water concentrations are around and what the water tables are there as well. So, yeah, this was focused on workers unite.
Right. Yeah.
If there are 12,000 wells in Midland, and if there are many big oil companies to make money, then theoretically they can separate uranium to He and to make it to
No,
5.
I don't think you can separate the uranium-238 and thorium. That's in the geological formation. But there are many papers out there of trying to go ahead and to extract out just the uranium-226. But again, this is everything from tabletop to actually what can be done in very large.
I think we might be closer. Well, I don't know, to million wells out in the West Texas, certainly Texas as well. Here's a question. Well, here's one that you sort of answered. A quick one about O2, which is who enforces monitoring of radioactivity
The
wells
DCEQ.
in the state of Texas?
So it's
Texas
DCEQ,
Federal
yeah.
Environmental Quality, and then
Yeah.
outside it's state
Yeah,
based.
and it's not federally mandated by the US EPA. US EPA has other types of mandates, maybe less mandates these days, but they have some mandates as well, yeah. But typically radioactivity is monitored by each individual state.
Right.
And in Europe, it's kind of monitored, also monitored more by the European Union, the EU. They have certain. Okay.
So the question on.
Dr. Pryor?
Yeah, since the fracking fluids go down and they come back up, they slowly collect some of this,
They can, absolutely, yes.
so then that's being transported from location to location.
That can be as well. There's been a lot of work. I know Dr. Lynn Katz in environmental engineering has been looking at fracking, produce water as well.
So if it can go from location to location, what are the containment policies for that?
Right now, there are no real containment policies, not in Texas.
Are there specific processes during decommissioning?
If you look through the internet and you will see how many oil companies have, they get something contaminated or full of scale, they'll just leave it in the field and leave. These are called abandoned wells. They just close up shop and just leave.
They don't decommission.
They don't decommission.
It's abandoned.
Very well said. Thank you.
All right, go to one online here. Yeah. This is maybe sort of a clarification. You said the produced water is not yet being commercially treated for norms, but it's in the research lab. People have done this.
Yes,
Correct?
yeah. There is a lot that's been done in the labs. The problem is how do you get to be economically viable to go from the lab out into the field?
Right. And do the norm levels change over time in the production field, or
No,
the half-lives you said, or?
no, the half-lives are long and it's always being produced, right? As long as you have uranium and thorium in there, it's going to be there forever and after. Even if all oil wells go away, it's still going to be there. It'll always be produced. Now, it may not go into the petroleum oil to be extracted, but it'll be left underground.
Right, so most of this is not actually end up in petroleum or in gasoline.
Absolutely not, no. Well, check your gas. Just don't light a fire to it.
Yeah, this other question here, what are the main, I don't know, conferences or industry working groups that study this?
There is a huge, great conference called Norm Global. It's held every 2 years in Houston, Texas. You've heard of Houston, right? Just down the road. And as such, they have speakers from all across the United States, including some speakers from Texas regulators, and even have one person from Canada who will be talking about regulations out there. So there are many conferences worldwide which talk about the regulatory and what you need to do to make sure of safety considerations. That, to me, that's the most important thing. And I like to play around with my gamma rays as well,
I got one other question, what kind of, are there, especially contractor companies or some of the larger? oil and
There
gas
are
companies
many
take this
contractor companies out there. There are about, certainly within the Texas, Louisiana region, there are about three or four very large companies. And they do everything that I said out here, the jetting and the mechanical abrasiveness and all that stuff.
Very well, so mostly contracted out.
Yes. The companies, ExxonMobil and all the others, they're in the business of extracting the stuff out, separating, selling it. They don't necessarily want to be able to do that as well. So they get the contractors.
Anything else? Not? All right, so let's thank our speaker, Sheldon Landsberger.